One of the major topics within Chapter 3 is to use properties of calculus along with a little bit of algebra to sketch extremely accurate sketches of the graph of a function. And the first step towards doing so is to talk about where a function is what we'll call increasing and decreasing, and in a moment where is a function concave up and concave down. So first, what in the world do I mean by increasing and decreasing? So we have the technical definitions here. A function is increasing on some interval I if whenever you have x1 smaller than x2, the function output at x1 is smaller than the function output at x2. And what that means is that as you move to the right, your function is getting larger. So a very intuitive concept. When we look at this graph, we say, okay, we're getting bigger, so that's an increasing quantity. Likewise, we say you're decreasing if you get smaller as you move to the right. So I would be decreasing here because the graph is getting smaller as you move to the right. And what we would like to do is think from a calculus perspective, how can we determine where a function is increasing and where it's decreasing? And I'm going to make a very simple observation here. If I pick any point on our curve in the increasing portion, and we draw the tangent line there, the thing to notice about that tangent line is it has a positive slope. And recall that the slope of a tangent line is the value of the derivative. So wherever that function is increasing, the tangent line is going to have a positive slope, and hence the derivative is going to be positive. So where it's increasing, we have that f prime is positive. Now, similarly, if we look at where the function is decreasing and pick our favorite point and draw the tangent line, that tangent line is going to have a negative slope. And what that negative slope tells us is that the value of the derivative, where the function is decreasing, is going to be negative. And this observation is exactly what we need in order to use calculus to determine where a function is increasing and decreasing. So putting this together, the first derivative property tells us, kind of just to put our observations from the previous graph into words, is that if you're on an interval and the first derivative is positive, your function is increasing on that interval. If your first derivative is negative on an interval, then your function f is decreasing on an interval. So if I'd like to determine where the graph of a function is increasing or decreasing, what I need to do is find the first derivative and determine where it's positive, where it's negative. One of these inequality type problems we encountered in Chapter 0. So let's go ahead and do that for the function x to the fourth minus 4x cubed. So the derivative is 4x cubed minus 12x squared. And in order to determine where it's positive or negative, the first thing I need to do is figure out where it is equal to 0. So if I want to solve where this quantity is equal to 0, we note that both of the terms involve an x squared and a 4. So if I pull out a 4x squared, I'm left over with an x and a minus 3. So this will be equal to 0 precisely when x is 0 or x is 3. So we know where our function is equal to 0, so now we make this number line argument, and we think about what happens in between. In between these zeros, so to the left of 0, 0 to 3, or 3 to infinity, the function f prime will be entirely positive or entirely negative. And what I need to do is just pick some sample points. Think about plugging, let's say, -1, 1, and 5 in. So if we use the sample point -1, we will have 4 times -1 squared, which is positive, times -1 minus 3, which is negative. So positive, negative, and that quantity is going to be negative. So f prime is negative when we are to the left of 0. Between 0 and 3, we pick our test point, x equals 1. We plug that into f prime, so 4 times 1 squared times 1 minus 3. So positive, negative, so that's also less than 0. So we are negative from 0 to 3. And then to determine what happens after 3, we use this test point 5. So when x is equal to 5, 4 times 5 squared times 5 minus 3. That's a positive, and two positives multiplied together make a positive. And now we know exactly where our function is increasing and decreasing. So whenever the sign of f prime is negative, the function is decreasing. Whenever the sign of f prime is positive, the function is increasing. So putting this together, we could say that we are increasing, and I usually just abbreviate this, INCR, on the interval from 3 to infinity, and it's decreasing wherever that first derivative is negative. So that would be from minus infinity to 0. And notice I don't include 0 in the interval of decrease because that's where the function is equal to, f prime is equal to 0, union with 0 to 3. So we've determined our intervals of increase and decrease. Next up is to think about concavity. So similar to the first derivative property, we have something called the second derivative property. So as long as your function is continuous, you can differentiate it enough times. The thing to focus in on are these two bullets here. If the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down. And let me just graphically illustrate for you what concave up and concave down looks like. So concave up, we think of just something that's opening upward. And I will almost always abbreviate concave up with CU and concave down with CD. So this would be the example of what concave up looks like, and it would be concave upward everywhere. Concave down, we think something that opens downward. So concave down. But notice in the graph of a function, you could have intervals where it's concave up and intervals where it's concave down. So for example, in the graph that I've drawn here, it looks like you have this point right about there where if we go to the left of that point, we have the function opening downward, so we would say concave down. If we go to the right of that point, the function is opening upward, so we would call it concave upward. And this point kind of in the middle where you switch from concave down to concave up, we oftentimes will call that the inflection point, which I've abbreviated here by IP. So IP is an inflection point, which corresponds to a point on your graph where your function changes concavity. So it goes from concave down to concave up. So for this function that we just worked with a moment ago, let's go ahead and determine where it's concave up and where it's concave down. We have the first derivative, so we also need the second derivative. So f double prime x is going to be 12x squared minus 24x. And I want to know where is this equal to 0. So both terms have a 12 and an x in common. And when I pull that out, I have an x minus 2 left over. So x equals 0, x equals 2. And now we go ahead and we play the same game again where we make a number line and we think about what's happening to the left of 0, between 0 and 2, and bigger than 2. So this would be the sign of f double prime. And after doing this for a few functions, we don't necessarily have to write down our sample points and what their values are going to be, but we can kind of just think about this intuitively. So looking at f double prime, if I plug in a negative number, like say -1, you are going to end up with a negative times a negative. So f double prime is positive when you are to the left of 0. If I plug in something between 0 and 2, say the number 1, you will have a positive times a negative, which is negative. When you are bigger than 2, let's say the number 10, you have a positive times a positive, which is positive. So looking at the sign of f double prime, wherever f double prime is positive, we are concave up. Wherever it's negative, we are concave down. So we have two intervals where we are concave up. That would be -infinity to 0 and 2 to infinity. And we have one interval where we are concave down, 0 to 2. And a very important observation when you're determining concavity, it's the sign of f double prime that you are interested in. So we find that second derivative, set it equal to 0, and figure out what happens in between those zeros. Now, a common question, working towards this big picture type of problem, which is using calculus to sketch a graph, would be to take what we've learned, the intervals of increase, decrease, concavity, up and down, and just use this to provide kind of a rough sketch of the function. So what we have learned, I've put all the information up here above, is our function is decreasing from -infinity to 0. So I usually kind of encode this above. So -infinity to 0, we are decreasing. From 0 to 3, we are also decreasing. And from 3 to infinity, we are increasing. We are concave up from -infinity to 0, and from 0 to 2, we are concave down, and from 2 to infinity, we are concave up. And what I would like to do is go ahead and sketch a function that satisfies these properties. And I'm going to note just by inspection that we can see what the x-intercepts are going to be. This expression is equal to 0 when x is 0 or 4. So I'm going to just go ahead and put 2 points on my graph. I know that an x-intercept at 0 and x-intercept at 4. So I'm going to go ahead and just sketch. So from the left, I'm decreasing, concave up. So decreasing, concave up. When I get to 0, I continue to decrease all the way over to 3, but now I'm concave down. And I switch concavity from down to up at 3. So I'm concave down, I'm decreasing, switch concavity to up, and once I hit 3, I start increasing, and I'm concave up. So this would be a rough representation of this function f of x. And once again, to note those properties, I'm decreasing and concave up. Once I hit this point, I'm still decreasing, but now I'm concave down, so opening downward, and it's subtle, but it's there. Then at 2, I become concave up the remainder of the time, but I keep decreasing and then increase. And these sketches do not have to be perfect, far from it. They just have to include that relevant information. So let's look at one more example here where we can just tie everything together. So for the function 2 plus 3x minus x cubed, let's determine everything. Intervals of increase, decrease, concave up, concave down, and then put it together for a rough sketch of the graph of the function. So to find those intervals of increase, decrease, the first thing I need to do is find the derivative. So term by term, 3 minus 3x squared, and I would like to know where this derivative is equal to 0. So looking at each term, the only thing in common is a 3, and when I pull that out, we have a 1 minus x squared left over. And 1 minus x squared, as we've seen multiple times here, is equal to 0 at plus or minus 1. So in terms of this function f prime, I'm going to make a number line, and I have 3 possible intervals: to the left of minus 1, in between plus and minus 1, and to the right of 1. And what I need to determine here is the sign of the function f prime. So if I plug in a large negative number, in this case it's say minus 10, we would have 3 times 1 minus 100, which is negative. If I plug in x equals 0, that's a very nice test point between minus 1 and 1, you end up with just 3, which is positive. And if you plug in a large positive number, let's say 10 again, you will end up with something negative. So putting this together, our function is going to be increasing on the interval from minus 1 to 1, and it's going to be decreasing on the interval from minus infinity to minus 1, along with 1 to infinity. So we've now determined the intervals of increase and decrease. The next thing we need to do is put this together with the concavity. So what is the second derivative? So f double prime of x is going to be minus 6x, and we need to know where is minus 6x equal to 0. The only place this is equal to 0 is at x equals 0. So in terms of the concavity on our number line, the only point we have labeled here is 0. That gives us 2 intervals, to the left of 0, to the right of 0. And what we need to determine here is the sign of f double prime. So if we plug a negative number into minus 6x, we get back something positive. If you plug a positive number into minus 6x, you end up with something negative. So we are concave up on minus infinity to 0, and we are concave down on 0 to infinity. So now that we've determined these intervals of increase, decrease, concave up, concave down, let's go ahead and put together a rough sketch of our function. So just to encode all of that relevant information, we said we are decreasing from minus infinity to minus 1, increasing from minus 1 to 1, and decreasing from 1 to infinity. And then we saw that we are concave up when we are to the left of 0, so concave up, and we are concave down when we are to the right of 0. And what I would like to do is sketch a function that is meeting these characteristics. So roughly speaking, I mean, one thing that we could do is find the zeros, and by inspection, or maybe even just doing a bit of algebra, we can see that one of the x-intercepts is going to be minus 1, and if we plug in 0, we get an output of 2. So I'm just going to go ahead and label that point 0, 2. So to the left of minus 1, our function is decreasing, concave upward. So decreasing, concave upward. Once we hit minus 1, our function switches from being increasing to decreasing to increasing. So we remain concave upward and we're increasing, But once we get to 0, we continue increasing, and we keep, and then we change our concavity to concave downward, excuse me. So concave downward, and we keep increasing until we get to 1, and then we switch from decreasing but remain concave downward. So a very rough sketch, but it shows roughly what our function is going to be looking like. So to the left of -1, we're decreasing and concave upward, increasing and still concave upward. We switch to concave downward, and at 1 we start decreasing.